like with any lesson, we want to start with a warm-up, something to get our brain kind of thinking of what exactly we're going to be teaching in this lesson, drawing from the stuff that we already know. So the first one is write an expression of tangent in as many different forms that you can come up with. So a lot of times students will, obviously, they think of the obvious, that they remember that, well, I remember the tangent of theta, going back from our geometry days, that is going to be the opposite over the hypotenuse. And then students were like, oh yeah, but I remember also in trig that in the last lesson, we also dealt with when we have a coordinate point on the unit circle, that we can represent tangent of theta as y over x, right? And that is good. So the thing about identities is an identity is basically just going to be an equation where we're going to have the left side is equal to the right side. Now, the thing is, the identities, they don't have to look exactly the same, right? They're just the values have to be equal or true. So like the left side, you could have 10 minus 5, and on the right-hand side, you could have 5, right? The left and the right, they don't look the same, but they are an identity because the left side is equal to the right side. So that's basically what we are going to start with, is some basic trigonometric identities, and then we're going to use that to simplify trigonometric expressions. So the first identities we're going to look into is the quotient identity. So the tangent of x is sine of x over cosine of x, and cotangent of x is cosine over sine. So let's just do a quick review of like where these come from, like why we have these, because it actually come from stuff that we can basically reason with and understand rather easily. So if we think about the first quadrant on the unit circle, and we say, all right, well, if I have a point, right, x comma y, we know that the distance from the origin to that point is going to be 1, right? Because the radius circle has, the unit circle has a radius of 1. And we'd say, all right, well, this is going to be our theta. And we know that we could also create a right triangle from this, right? That's how we created the unit circle. So this would be represented as x, and this would be represented as y. Now, the important thing that we can look at with this is we know that if I was going to look at this triangle, and I go back to my original definition here, tangent of theta is opposite over hypotenuse, or also we could say tangent of theta is y over x. So if I say, all right, tangent of theta equals y over x. Now, how are we going to get to the sine of x and cosine of x? And that's where it comes into like, oh yeah, I remember when we were evaluating, right, on the unit circle, remember the sine of theta was equal to y, the cosine of theta was equal to x. So now I can just use some substitution here, and I can say, well, if tangent of theta is y over x, I can also rewrite that as y as the sine of theta, and x as the cosine of theta. And therefore, you can see how that identity makes sense. And then you can see cotangent, that's just going to be the reciprocal of that cotangent identity. Now let's get into the reciprocal identities. Now the reciprocal identities, again, is very similar with our understanding of special right or just right triangles. So if you think about the sine of theta, right? If you remember that was opposite over the hypotenuse. Now, again, if you kind of think about going on the unit circle, we could rewrite that as the sine of theta, the opposite side, right? That was going to be y, and the hypotenuse is 1. And then the sine of theta was just represented as y. Now, similarly, if we think about the cosecant, and the cosecant of theta, then it was going to be the hypotenuse over opposite, right? Those are reciprocals of each other. And so therefore, when you think about this in terms of y, then this is going to be a 1 over a y. And then if you want to look at how cosecant then is going to relate with sine, we can just rewrite a cosecant of theta, or I'm sorry, a y as a sine of theta. So you can see the cosecant of theta is simply just going to be a 1 over a sine of theta. And you can see that's how that one goes and works out. And then over here, you can see how they just go back. So if I have the cosecant of theta is equal to a 1 over sine, like how am I going to get back to sine of theta? Right? How can I get this now relationship to now solve for sine? Well, if I wanted to solve for sine, I would have to get it off the denominator. So you multiply sine of theta on both sides. And then what you would have here is going to be a sine of theta times a cosecant of theta is equal to 1. And again, if we wanted to solve for our sine of theta, we divide by cosecant of theta, divide by cosecant of theta. And now what you can see is we'd have a sine of theta is equal to a 1 over a cosecant of theta. So I worked with this for sine, but ladies and gentlemen, you can do this for the cosine as well as do this for the tangent. So you can see how these reciprocal identities are going to work and that they are true. Now, the next one is going to be even odd identities. Now, a lot of times students kind of get these even odd identities like messed up. They kind of forget, like they don't understand how they can work. So I'm not going to go through all of them, but what I want to do is just kind of show you looking at the graphs. And if you can understand, if you can remember what the graphs are going to look like, in my opinion, it's a lot easier to remember these identities. So let's go and first look at the sine function. If you're going to look at the sine function, and let's see, we have initial period that looks something like this, and then go over like that. Okay. Now you got to remember what happens when we take the reflection. Actually, well, let's just look at this point. Well, let's look at this point right here. So that point, look at it right there. All right, that point is going to be at a pi halves, if you remember from the unit circle, and graphing. So this coordinate point is at pi halves, and remember the y-coordinate is going to be at 1. So what they're saying is, well, what about at negative pi halves? So if you look at negative pi halves, so this would be at negative pi halves, what is our value? Our value is going to be at negative 1. Right? So you can see when I take the sine of a negative angle, so instead of sine of pi, we know is at 1. Sine of negative pi, you can see, is also going to be at negative 1. Now again, that's going to be true for the exact same thing, even if I was to look at the cosecant graph. If we were going to draw this exact same graph, and we were going to do the cosecant function, remember the cosecant function is just going to be these reciprocals of these graphs, right? And we have some asymptotes right here. And then you'd have that point right there, and it's going down. So again, what I want you to see is, let me actually just write this out. If I have the sine of pi halves, that's equal to 1. The sine of negative pi halves is equal to a negative 1. And ladies and gentlemen, this is true, the exact same thing over here. If I say the cosecant of pi halves, that's going to equal to a 1, right? You can see that value is right there. And the cosecant of a negative pi halves is going to be equal to a negative 1. So we're dealing with the sine, the cosecant. Whenever we're taking the negative of that angle, the value is going to be the exact same. It's just going to be the negative version of that. Now, we can also look at this in terms of like the cosine graph. Because hopefully you remember like the cosine graph, well, yeah, that looks very, very similar to the sine graph, right? So now in this one, it has a vertex over here, and it's going to go up and down in this case. And then over here, we can go down. All right. Now in this case, rather than looking at pi halves, let's go and take a look at pi. So pi would be roughly in this end. So that's pi halves. There would be pi. And then pi halves would be over here. What I want you to see is when I say, what is the cosine of pi? That's equal to a negative 1, right? Cosine of pi, that's equal to a negative 1. Well, what about the cosine of negative pi? You can see, ladies and gentlemen, they have the exact same y value. These are symmetrical about the y-axis. So the cosine of, sorry, I should probably use parentheses there. Cosine of negative pi is also going to equal to a negative 1. And ladies and gentlemen, we can again do the exact same thing here with the secant graph. All right, because again, remember the secant graph is just going to be the reciprocal of that. So it's going to look something like this. So you're going to have here, and then you're going to have these points here, and you're going to have some asymptotes. Asymptote looking right there, and an asymptote looking right there. But again, the exact same thing that I want you to see. If I take the secant of pi, that is simply just going to equal to a negative 1. And the secant of negative pi is also going to equal to negative 1. So the important thing when looking at this, when you're looking at the cosine and secant, so cosine and secant are the only time when you take the negative angle, you're just going to get that exact same, you're going to get the exact same as the original. So if it's a cosine of negative x, it's the exact same as a cosine of x. All right. But however, sine, cosecant, tangent, and cotangent, which I don't have enough room to show you graphically, but hopefully you can see they're exact same thing. Now, the next one is, again, something I think we can easily kind of remember, but sometimes, a lot of times, students get tricky because it looks confusing, right? You look at this and you're like, what the heck is going on? Sine of pi halves minus x is equal to cosine. So again, what I like to describe this to my students is to remember, ladies and gentlemen, these are transformations on a graph, right? If you're going to take a look at this pi halves minus x, right? What exactly transformations are going on? Well, what we could do is we could rewrite this as a negative x plus a pi halves, and then we could factor out that negative. So therefore, that's a x minus a pi halves. So what's actually happening to the graphs? What we're doing is we're reflecting it about the y-axis, and then we're shifting it pi halves to the right. So again, let's go and take a look at the sine graph and kind of see, well, how does this then work? How can we see that the sine of pi halves minus x is going to equal to cosine? So again, let's just draw a quick little sketch of this sine graph. And when you do that, let's see, you got this. We're not going to be perfect. That's not the sine graph. So we're not even going to be worse than perfect. We're going to be wrong. We don't want to do that. All right, let's just take the initial period, okay? So if I take this initial period and I reflect this graph about the y-axis, right? Basically what you can do is you can think about this graph is now going to look like this, okay? And then if you shift it pi halves over to the right, look what's going to happen. Now this graph looks like it's going to be the tangent graph. And what I want you to see is, yeah, that's exactly right. What's happening now is when you reflect it and then shift it pi halves to the right, you now have the exact same graph as the cotangent graph. So let's go and take a look at, if you can see that, that's exactly what's going on there. So let me actually just rewrite this. So I'll have, so if this was going to be this would be y equals a sine of x. And then if we're going to apply those transformations, then you can see that this graph is now going to look like the cosine graph. So y equals a sine of pi halves minus x. Okay, and that actually is the exact same thing as y equals a cosine of x. So the way that I like to remember these is I like to remember them by their groupings. If the graphs look the same, then what we call these cofunctions are going to be exact same. So we know sine and cosine, right, are very similar to each other. I can't go from sine to cosecant, right? Or I can't go from sine to like cosecant of this. So you can see like this has asymptotes, this does not, right? This is continuous, this is not. So I can't apply some transformations to go from a continuous function to a non-continuous function. So we know that the cosine and cosine are going to be grouped. In similar fashion, tangent and cotangent are going to be grouped. And that's why we have the cosecant and secant are going to be grouped. So we could apply these exact same transformations to the graph of cosecant and secant, and we'd get the exact same thing. Now, let's go and take a look at least the tangent graph, just to kind of see again, like make sure, like, all right, I think I believe you, Mr. McLogan, but let's just take a look one more time on this cotangent graph. So if I had, let's see, y equals tangent of x, I know the initial period of that graph is going to look something like this. So we know it kind of looks like that cubic function, right? We're going to have a asymptote here, and the asymptote, remember, is at pi halves. And then we're going to have another asymptote over here, and that's at negative pi halves. Okay, so let's go and see what the graph of y equals a tangent of pi halves minus x, or if we just like apply those transformations, you know, add shifting it to the right and reflection. So if we looked at this, let's see, pi halves minus x. Okay, so again, take this graph, right? If we reflect it about the y-axis, it's going to look like this. Now, let's shift it pi halves to the right. So I'll take this little thing here. I'm going to take this. If I move this pi halves to the right, then wow, that looks very, very similar to what the tangent graph would look like, right? Because the tangent graph, if you recall, or I'm sorry, cotangent graph, the cotangent graph has a y-intercept at pi halves. It has an asymptote at pi. And yes, ladies and gentlemen, that graph, it's not perfect that I have here going on, but that, boom, is exactly what we're looking at for the cotangent graph. So you can see how they relate. So you just got to think about these as the transformations. That's the important thing that I want you to remember for those. And if you can just remember what the graphs, which graphs are similar to each other, it's really easy to remember these cofunction identities. All right, last but not least is going to be the Pythagorean, and then we're going to get into some examples. Now, to remember the Pythagorean, there's a couple things. I remember when I was in school, and I was taking precalculus, the one thing my teacher was like, you got to know this identity. You got to remember it. And I remember when I first started teaching precalculus, I was like, man, I forgot so many things on precalculus. But the one thing I didn't forget was sine squared plus cosine squared of x, of cotangent of x, of x is going to be equal to 1. All right. So again, let's go and take a look at what that is. So we know this coordinate point, this is going to be a xy, and we know that the radius or the distance from there is going to be 1. We could say this is going to be our theta, and we know we can create a right triangle because that's how we created the unit circle. And we could say, all right, that is going to be your x, that is going to be your y. Now, a couple things we need to remember. If we were going to use the Pythagorean identities, we could say we could create a Pythagorean relationship here, right? We could say that the x squared plus y squared is equal to 1. Whenever we have a right triangle, we know we can use the Pythagorean identity. So the important thing, though, to remember is going back to our understanding of x and y with cosine and sine. Remember that the x is the same thing as the cosine of theta, right? We already made that substitution. And y is the same thing as the sine of theta. So by using our understanding of coordinate points on the unit circle, x, y, as cosine of theta, sine of theta, if we just now replace this x with the cosine of theta and this y with the sine of theta, ladies and gentlemen, we now have the Pythagorean identity. So this is going to be the cosine of theta. What am I writing? Tablet's being a little iffy. So we have the cosine squared of theta, which is how we write it. We don't write it as cosine theta squared because then that kind of treats it as like the theta is squared. So you can use parentheses and say cosine of theta quantity squared, or you can just write the squared right after the cosine. And then plus here we'd have a sine squared of theta is equal to 1. Now, the definitions that I used here was x, so x is representing the angle in these definitions, whereas here on my diagram, theta represents the angle. So that's the difference. All right, now you might be thinking, well, cosine of theta plus sine squared of theta is equal to 1. I got that. How are you getting these? Well, again, just like we did some algebraic manipulation in the reciprocal identities, we can do that over here too. So if I have the cosine squared of theta plus the sine squared of theta, and we know that's equal to 1, right? Now, if I want to be able to, let's say, divide everything, as long as I'm doing everything on the same side, and then I'm just creating an equivalent equation. So if I go ahead and divide everything by, let's just rewrite it like this. If I divide every term, both sides, by cosine squared of theta, let's see what's going to happen here. So that's a squared. And then if I divide this by a cosine squared of theta, and then this by cosine squared of theta, I would now get a 1, right? Cosine squared of theta plus divided by cosine squared of theta. It's the same thing divided by itself. It's going to equal 1. Over here, we know that's the quotient identity. Sine squared of theta over cosine squared of theta is now going to be a tangent squared of theta. So that's a tangent squared of theta. And then via the reciprocal identities, 1 over cosine squared of theta is now equal to a secant squared of theta. And you can see that is that one right there. So again, hopefully you recognize, well, Mr. McLogan, can we do the same thing with sine? Of course we can. So why don't we just go ahead and do that? So again, we take our original Pythagorean identity, which hopefully you are not going to forget, and then we just do the same thing. Instead of dividing everything by cosine, now let's just go and divide everything by sine, or sine squared of theta. So I take the sine squared of theta, divide this one by sine squared of theta, and take this one and divide it by a sine squared of theta. Now over here, again, using our quotient identities, cosine squared over sine squared of theta is going to be a cotangent squared of theta. Same thing divided by itself, we know it's going to equal to 1. And again, the reciprocal identity tells us this is equal to a cosecant squared of theta. Now, ladies and gentlemen, be a little careful, or just recognize here, this is as 1 plus cotangent squared of theta. This is going to be cotangent of theta plus 1. It's the exact same thing, right? 2 plus 3 is the same as 3 plus 2. And the thing about identities, which I mentioned at the beginning, things don't always have to look exactly the same, right? And that's really, really important. And sometimes it's a mental shift for students to have to be able to take once we start getting into examples, is this understanding of things can still be exactly the same value, but they don't have to look the same. Now, obviously, you could just go ahead and rearrange that on the cubic proper, but it's important to see we're going to be doing some manipulations so that we can simplify these trigonometric expressions.